Okay, in this first question, we are supposed to prove that the given operator is bounded linear operator, and also we have to evaluate its operator now. First of all, let's look at what does this operator exactly does to the elements in the domain. First of all, the operator acts between two sets which the domain is the continuous functions between a and b. A and b could be any two real numbers, so this is the set of all continuous functions, and the codomain or the range is real numbers. So basically this is a function or rather operator uh, which takes any continuous function between a given two real numbers. Let's say, for example, let's say it is 0 and 1. So imagine a set of all continuous functions between 0 and 1. I'm taking a specific example for this to explain. So uh, what does this operator does is exactly it takes one continuous function from the given domain, and it assigns a real number to it. It's kind of a, it takes the operator T takes a continuous function and gives a real number attached to it. So this operator is defined to be this relation, which is T of f is equal to the integration or the Riemann integral of fx from a to b. So clearly this is a real number because the Riemann integration represents the area under the curve. So this is clearly a real number. So f is a continuous function between a given two real numbers, let's say a and b. So first of all, we have to prove that the given t is linear. For that, we take any generic two continuous functions from the given domain C of AB, and uh, we evaluate the t of f plus g. So if we can prove that the sum of these two functions equal to the summation of individual terms when applied to t, we can say uh, it is a part, it actually one part of proving the linearity. So t of f, t takes f plus g, and by the definition it is the integration of f plus g from a to b. Then uh, simply the summation of functions, we can separate these two terms and write fx plus gx, and by the Riemann integral rules or the rules of Riemann integration, we can separate this integral to two parts. So we will end up having this relation. Then we take any a which is an element of underlying scalar field. It could be a could be a complex number or a real number. So don't confuse that this a is not this a. I could have used a different letter for this one, maybe alpha. So don't confuse with this a and this a. This if you're following these notes, please consider this as alpha or some another symbol. So again, we have to apply the definition for this one, which is the integration of a to b of this specific function. Again, by the properties of Riemann integrals, we can take the constant term out because this is a scalar, either a complex number or a real number. So we will end up having this relation. Since the operator t satisfies these two relations, we can say this is linear. So one part is done. So our next claim is that t is bounded. So what does that it means by a bounded operator? So if t is linear, and if there exists a positive constant, which is let's say c, such that the norm of the image is less than or equal to the constant times the norm of uh, the pre-image, or rather the element from the domain, we say that T is bounded. So basically, the norm of image and norm of pre-image has to be in this order, or rather, it has to satisfy this uh, inequality. Okay. So first of all, what is the norm of image? So image comes from real numbers. So uh, the general norm of the real field is the absolute value. So norm of t of f is equal to the uh, absolute value of this image, which is absolute value of this integration. By the Riemann integral properties, we can uh, put this absolute value inside of the function, inside of the integral, sorry. So by relating this is by relating this, by ordering this uh, by ordering this way. Okay. So again, the norm of image is basically the absolute value of this t of f, because this images comes from the real field. uh, by the definition, again, we can replace tf by this integral, because tf t of f is equal to this integral. Then uh, we can relate these two by using the properties of Riemann integral, by putting the absolute value inside of the integration. So our first equation is this, or rather the first inequality is this. Then we have to evaluate this norm, which is the sup norm, because the question gives us that the C of this domain is equipped with the sup norm. Sup norm is the uh, supreme denoted by this symbol infinity, and uh, it is by the definition supremum of all the absolute values of this function, which is in the given range, that is a to b. So we know that the supremum is greater than any element of absolute value of fx, because supremum is the largest element. So we can replace by the first inequality, we can replace this absolute value of fx by the supremum of fx, and we have to relate those two by greater than or equal sign, because supremum is always the greater than the given element. So the supremum of absolute value of fx basically means the norm of subnorm of f. So subnorm of f is the norm is always a constant positive integer, so we can take this out from the integration, and we can just integrate this a to b. uh, this is a constant, so once we integrate, we will ended up having x with boundaries a to b, so which means b minus a. So by the definition, in order to be bounded, we have to find a positive constant. So in this question, we don't know about this quantity, whether it is positive or negative. So rather than putting c is equal to b minus a, we have to take the absolute value, so that it does align with the given definition. So okay, now we have proved that t is also bounded. So here now we have proved that t is a bounded linear operator. Now remain to prove that the its operator norm is uh, now it's remain to evaluate evaluate what is the operator norm. Okay, so in order to find the operator norm, if this inequality holds, and if we can find a vector in in the domain which satisfy the equality, which means if you plug x naught to this inequality, it becomes an equality. So if we can find such a vector in the domain, we can directly say the operator norm of this function, or rather the operator, is equal to this constant c. Okay, now our goal is to find a continuous function which satisfies the equality, not the inequality, the equality. If we can find such a uh, continuous function, we can say the operator norm is equal to c, which is the b absolute value of b minus a. Okay, so in such cases, we always take the very primitive continuous functions. So here I take as f naught x equals 1, which is a constant function for all x in AB. So simply you can evaluate the integration and you will ended up having uh, absolute value of b minus a. So, and also it is very convenient and very straightforward to see that the subnorm of this function is 1, because it is a constant function. The maximum value also is 1. Therefore, the supremum is 1. Okay. Since this is 1, subnorm of f naught is 1, and this is equals to b minus absolute value of b minus a, this inequality becomes equality. So the equality holds for f naught x, which is equal to x. Therefore, we can say the operator norm of t is equals to absolute value of b minus a. So it is that simple, because in order to evaluate the operator norm, we only need to find a vector from the domain which satisfies the given equality, not the inequality. We have to find a vector from the domain which satisfies the equality. Therefore, if such happens, we can say the operator norm is equal to this constant c. In our question, this constant c is equals to absolute value of b minus a. Okay, that is how we prove an operator is bounded and linear, and also that is how we prove the operator. That is how we evaluate the operator now. Okay, now this question is a kind of different one. Uh, the differential transformation from P01 to itself when P01 is equipped with the subnorm is unbounded. In this question, we are asked to prove that the given operator is unbounded. So how do we do that? First of all, this P01 is all the polynomials, which is a subset of continuous functions C01. Therefore, P01 is a subset of C01, and P01 contains all the polynomials. Okay, and the question is given to us that this domain and codomain are the same, because it says P01 to itself and it is equipped with the subnorm. Okay, what is the differential transformation? Differential transformation is the operator takes uh, a polynomial from the domain and it differentiate the given polynomial, and it gives another polynomial from the domain, or rather the codomain, because both are equal. Okay, it's straightforward to see that this is a linear, because you can easily follow these two steps to verify this is a linear function. So what most important is that we assume here, as we are trying to prove this by a contradiction, we assume t is bounded. Okay, since t is linear and t is bounded, because of the assumption, there exists the positive constant c such that this equality holds, which is the image of the norm and the norm of the image and the norm of the pre-image are related by a constant and this ordering, which is a less than or equal sign. So this is our assumption because we assume t is to be bounded. Okay, now we have to come up with a specific polynomial in P01 which contradicts our assumption. So this is a very classic example. We take the polynomial to be x to the power n. So for all n greater than or equal to 1. So what is the norm of subnorm of this one? Subnorm of this one means supremum of x to the power n. So here x to the power n is not just one polynomial, it's a family of polynomial. When n is equal to 1, you get a straight line. When n is equal to 2, you get a curved quadratic part of the quadratic function, which is fpn p2 is equal to x squared. When n is equal to 3, you get a quadratic function. Likewise, this is a family of polynomials. But most important part is this, that since this is goes from 0 to 1, it's always the maximum values is 1. So therefore no matter what is the n value is, no matter what's the n value is, you always get the supremum of this function as 1. Now take the norm of image, which is you have to differentiate this one easily, n to the power x n minus 1. Since n is constant, you can take n out, and the supremum of x to the power n minus 1 is also n. Therefore you will ended up having this one n. Now you have an answer for this one, the norm of the image. You have an answer for uh, norm of pre-image. So you have an inequality. Now substitute each of these answers to the uh, assumption or the assumed inequality. So you will ended up having n is less than or equal to c times 1, which is n is any natural number. This inequal to say that natural numbers is bounded, which contradicts the Archimedean property, because natural numbers are always unbounded and there does not exist any positive integer which is greater than all the natural numbers. Therefore, our assumption is wrong, which is t is unbounded.